what we're going to look at in this video is measures of variability. And really that's just a fancy way of saying measuring how spread out our data is. We'll start by looking at two different data sets. Here we have data set 1 and data set 2 that are already nicely arranged in an array for us. If we were to go and calculate our measures of central tendency on these data sets, what we would find with both of them is that they both have a mean of 6, a median of 6, and a mode of 6. If all we're to look at is those measures of central tendency, we might be fooled into thinking that these data sets are identical. To look at the distribution of the two data sets, we can see that one data set is quite a bit more spread out than the other one is. We can see that our data set number 2 is much more compact than data set number 1. So while we have the same measures of centrality, if we were to take the measures of variability, we would see that they are actually quite different, these two data sets. And as we said, what we're talking about with measuring variability is really just how spread out or how scattered the data actually is. The three measures of variability that we will study here are the range, the standard deviation, and the interquartile range. We won't do a whole lot with the range, and we've actually already discussed it in our lecture about frequency distributions. The range is simply the difference between the largest number and the smallest number. So if we took the range in data set 1 here, high of 350, low of 250, the range is 100. As is our range in data set B, 350 minus 200 gives us a range of 100. But just looking at the histograms of each of these data sets, we can see that they're actually much different in terms of their variability, and the range really doesn't help us distinguish between which of those is more spread out. It simply tells us what the spread is between the high and the low value. We'll look now at our second measure of variability, which is standard deviation. Standard deviation is a measure of variability that is based on deviations from the mean. We learned in our lecture of measures of central tendency what deviations from the mean was, simply how far each data point was from the mean. If we're to look at these two formulas and try to think about which one refers to population data and which one refers to sample data, we remember that for population data, we generally have Greek letters and capital letters from the English alphabet, whereas with sample data, our formulas involve simply lowercase letters from the English alphabet. Where we have Greek letters and capital English alphabet letters, we are referring to population, and where we have all lowercase English alphabet letters, we have a sample formula. Our two new symbols, we have sigma for population standard deviation and S for sample standard deviation. All of the other symbols we saw in our lecture of central tendency. X, capital or lowercase, refers to an individual data point. N, capital or lowercase, refers to the total number of data points. Mu refers to the population mean. X bar, the sample mean. Now, in our measure of central tendency lecture, our formulas, the only difference between them was pretty much cosmetic. The math was all the same. Now we see here that as we're talking about population data and sample data, there is a difference in the formula. And both of them, we're taking the individual data points minus the mean, squaring it, and adding it all together. Individual data point minus the mean, squaring it, adding it all together. However, when we're done that, with population standard deviation, we divide by the entire population size. With sample standard deviation, we divide by the sample size minus 1. So now there is a mathematical difference between these two formulas. So recapping those symbols. From our measures of central tendency lecture, we learned that mu referred to population mean, x bar referred to sample mean, x an individual observation, and n the total number of observations that we have. Let's look at an example and calculate the appropriate standard deviation. If we were to say that the following data represents the number of hours that 5 students from this class spent on stats homework last week, and we're to calculate the appropriate standard deviation, the first thing we would have to determine, because there is a fundamental difference in the two calculations, is whether we're dealing with population or sample data. So in this case, it is sample. 5 students is not our entire class. It is simply a subset, a random sample from that population. So we will need to use our sample standard deviation formula. One way you may find it easier to make this calculation is to look at what appears to be the fairly ugly part of this formula and break it down into its simple steps. If we think about the rules of BEDMAS every time we do a formula, what we will have to do first is we have a series of brackets, then we'll deal with the exponents, and finally deal with the addition. Remember, the symbol always represents the sum of. So BEDMAS lets us know brackets, then the exponents, then the addition. And if we're to break down that big ugly part of the formula into its little bits and pieces, really all we're doing is inside the bracket subtraction. We can all handle that. Then squaring a value, that shouldn't be a problem. And then simply adding them all up. But in order to do any of that, the first thing we're going to need to calculate is the mean. So remember, the mean comes from simply adding all of our data points together and dividing by the total number of data points. So in this case, we have a mean of 6. Now let's break down what seems to be that ugly bit of the formula into its bits and pieces. We'll deal with the individual observations first. Then within our bracket, we have the individual observation minus the mean. So 5 minus my mean of 6 is -1. 8 minus the mean of 6 is 2. So on and so on down the road. Once we've done all the operations within the bracket, we can go on and square those values. -1 squared is 1, 2 squared is 4, -2 squared is 4, and so on. Then really the last thing we have to do in terms of the numerator is summing it all up. So 1 plus 4 plus 4 plus 9 plus 16 gives me a numerator of 34. And the denominator, simply our sample size of 5 minus 1. And once we've done that division, we can take the square root of the whole thing, and getting that we have a standard deviation of approximately 2.92 hours. Well, what does that really mean to say that we have a standard deviation of 2.92 hours? For now, all we have to know is that when we talk about standard deviation, it is a score of variability. So how spread out our data is. So if I was to compare this standard deviation to another data set standard deviation, the one with the higher standard deviation would be more spread out. So the more variable our data set is, the higher the standard deviation. Some formulas that we may use later in this course may use the squared version of standard deviation. That squared version of the standard deviation is called the variance. So because it is the standard deviation squared, we use the exact same symbol that we did for population standard deviation and sample standard deviation. We simply square it to get the population variance or the sample variance. And really the only thing we would have done differently in our calculation is in the last example we did, we would not have taken the square root. We would have simply had a sample variance of 8.5. Looking at how standard deviation is affected by outliers, going back to the same data sets that we were looking at in our lecture of measures of central tendency, if we were to calculate the standard deviation for each of these data sets, data set 1 would have a standard deviation of 1.95, whereas our data set 2 with simply one number difference, we would have a standard deviation of 16.16. So we see that here, the standard deviation is drastically affected when we have outliers. And the reason for that is because, remember in that calculation, we're taking each of those individual data points, we're subtracting the mean, something that's already affected by outliers, and then we're squaring that. So we're compounding the effect that those outliers have in this calculation. So again, we'll need something to use as a backup when we have a data set that has some significant outliers. So what we have for our backup plan when we do have those extreme outliers is the interquartile range. The interquartile range requires some knowledge of how percentiles work. What we mean by a percentile is if I'm talking about a specific percentile, for example, the 90th percentile, what it means is that 90% of the data is below that value. So for example, at my son's 2-year checkup, the doctor told us that Cole was in the 90th percentile for height and weight. Well, what did that mean? It meant that he was taller and heavier than 90% of the other 2-year-olds out there. P for percentile with the subscript 46 would mean that we're referring to the 46th percentile. To calculate percentiles, you will notice doing this by hand is very, very much like doing the median. What we would have to do is arrange our numbers from smallest to largest, find our percentile position instead of our median position. Just like percents, we're dividing our data up into 100 little pieces. So here we would take whatever percentile we're dealing with over 100 times n plus 1 to find the percentile position. And then we would count along our array to that position. What we should note here is that we will not do any interquartile range calculations by hand in this course. We will use Excel to do all of our calculations. Quartiles are really just a special percentile. If we're to think about how the first quartile relates to a percentile, and again, very similar to the notation for percentiles, except because we're talking about a quartile now, we'll use Q with the subscript 1 to represent the first quartile. How would Q1 relate to percentiles? Well, the first quarter of our data would represent the first 25% of our data. So Q1 is the same as saying P25. Similarly, Q3 is the same as P75. The third quartile is the same as the 75th percentile. How does the median relate? Well, if we think again as to what the median actually is, the median is the physical center of our data. So at that physical center, we have exactly half of the data below the median position and exactly half the data above the median position. Well, that's the exact same thing that the 50th percentile is. At the 50th percentile, we have 50% of our data below it, 50% of our data above it. Or another way of saying that is the second quartile. So if we ever hear the median, the 50th percentile, or the second quartile, those three things refer to the same measure. But what actually is the interquartile range? Where the interquartile range, we're looking at the spread in the middle 50% of our data. So our calculation is simply Q3 minus Q1. So why this isn't affected by those outliers is because we're eliminating the bottom 25% and we're eliminating the top 25%, and we're only looking at that middle 50% of our data. So when we have outliers, the interquartile range negates those.
Now to find out how to calculate our measures of variability with the use of Excel. So the first measure we're asked to calculate here is the standard deviation. And as always, a notice about what I am calculating. So to calculate standard deviation, again, we can go through our formulas, more functions, statistical, or if we simply start trying to type standard deviation. Even as we type ST, there are not many functions. So the first thing I see is standardized, which tells me it returns a normalized value from a distribution characterized by a mean and a standard deviation. Well, that tells me it needs a standard deviation to calculate what it's looking for. So that's not quite what we need. But the next two, we notice there's stdev.p and stdev.s. Now, much like when we did this by hand, it is absolutely critical to identify whether our information comes from a sample or a population, because there is a fundamental mathematical difference in those formulas. Right? With population, we're dividing by the entire population size. And with a sample, we're dividing by our sample size minus 1. So if we look, it should be pretty straightforward, I hope. The .p represents population, calculates a standard deviation based on an entire population. Or .s estimates the standard deviation based on a sample. So first things first, we have to identify, is this population information or is it sample? So it tells us here we're doing the quality assurance check on filling levels at this Coca-Cola bottling facility. And remember, for this to be population information, we would need every bottle that's ever come out of this facility. So clearly, this is not every bottle that's ever come out. This is simply a random quality assurance sample test that we're doing. So here we do have sample information. We'll use stdev.s. Highlight all of our data, hit enter, and we should get a standard deviation of approximately 0.43. Now, one thing with Excel, chances are that there is more decimal places with that, and this is why it's always a good idea to cell reference any calculations you've made. Now notice these buttons up here do not do any rounding. All they do is either increase or decrease the amount of decimals that they're showing. So if I wanted to increase how many decimals, I can see that this number actually has many more decimal places than the two that it initially displayed. So if we were to simply type in 0.43 to use that number in a future calculation, all our future calculations would be off because of that rounding we've done. So this is why I say we always want to make sure, as we do calculations in Excel, cell reference back to that previous calculation. Don't type in the number on your own. But for us, for the most part, we will default to 2 decimal places in our calculations. And I would list my final answer as a standard deviation of 0.43. Okay. Similarly, if I was asked to calculate the variance, I simply start typing VAR, and we notice, just like with standard deviation, we have a variance calculation based on an entire population and a variance calculation for a sample. So again, ensuring that I use the one for sample, highlight everything, hit enter, and we see we get a variance of 0.19. But again, there's probably many more decimal places associated with this, which there is. And also, if we remember that variance is just a squared version of standard deviation, we actually didn't even need to use that variance calculation. I simply could have squared my standard deviation, so to the exponent 2, and we should get the exact same answer. So if I displayed more decimals, regardless of how many decimal places we kept, both numbers are exactly the same. Okay? But again, for our purposes, if we were listing this as a final answer, we would simply represent that to 2 decimal places and a variance of 0.19. Okay, last but not least, we are asked to calculate the interquartile range. So if you remember when we calculated range back in our frequency distribution discussion, there was no Excel function for range. Similarly, there is no Excel function for interquartile range. It's on us to remember that the interquartile range is found by subtracting Q1 from Q3. So IQR equals Q3 minus Q1. Now, even though there isn't an Excel function for interquartile range, there is Excel functions to find the first and the third quartile. So I can find Q3 in Excel, and I can find Q1. So again, I'm just going to use equals and try first to just start typing quartile. We see that there is quartile functions. Quartile.exe and quartile.inc. All the calculations that our current textbook uses are based on the exe function, so we will always use quartile.exe. So using quartile.exe, again, I can see that there's multiple arguments in this function if I want to see what those arguments are. Right? As I highlight on array, it tells me array is the array or cell range that we're dealing with. Well, those are our data points. The next argument, quart, again, tells me that quart is a number with a minimum value 0. If I'm looking for the first quartile, I'm going to put in 1. If I'm going to put in the median, which is the same as a quartile or the 50th percentile, I'm going to put in 2. Quartile 3, I'm going to put in 3, and so on. So here I do want the third quartile. Hit enter. Similarly, I use the exact same function to find the first quartile, quartile.exe. Highlight all of the data. Second argument now is the first quartile. And to find my interquartile range, I will simply do a subtraction, Q3, or my cell where I calculated Q3, minus my cell where I calculated Q1. Hit enter. And to 2 decimal places, we get an interquartile range of 0.76. I'll make one further calculation in this data set, even though I'm not asked to do it in this case. It is for the percentile, and this is a function that is often used incorrectly the first time we try to use it. So if I asked you to calculate, say for example, the 60th percentile, which would be symbolized with capital P and a subscript 60. Okay, so if I'm looking for P60, remembering that capital P with the subscript number represents percentile, I'll look and see if there is a percentile function, which there is. And we see very much like we had a quartile exclusive and inclusive function, we have the same thing for percentile. So for percentile, I'm going to use the exclusive function again, and here I'm going to make the mistake that most people do make the first time they use this, is I'm going to highlight all of my data, and I see the next thing they want is K, and I remember back when I used the quartile function, it was either 1 for the first quartile, 3 for the third quartile, or whatever. So if I type in 60, I hit enter, and I see I get this weird notation. Anytime I see this, it's telling me that I've made a mistake in one of the arguments of that function. So it's seeing something that it doesn't expect to see. And the best thing to do, if ever I get this warning, bring up the function box. Again, go through your different arguments, because we'll have functions that involve 3-4 arguments starting in next unit. I look here, again, what is the array? Well, that's the range of cells. I'm pretty sure I highlighted the cells okay, and there wasn't an issue with that. If I look down at that second argument, K, what does it tell me K is supposed to be? It tells me K is the percentile value that is between 0 through 1. I typed in the number 60. 60 is in the number 0 through 1. All that percentile function wanted me to do is instead of representing 60 as its percent, I want 60% in its decimal form. So instead of 60%, I will put in 0.6, in which case I do get the appropriate 60th percentile returned to me of 591.6. 0.26 to 2 decimal places.
What we're going to look at now is something called the empirical rule. Now, this is a very, very important rule and is really the focus of the bulk of the rest of this class. It relates the descriptive statistics that we've been talking about to probabilities that we will be talking about for the next couple lectures, and how that's going to help us make decisions for inferential statistics in the future. This empirical rule applies only to data that is symmetrical. So saying it's symmetrical, we have that nice bell-shaped curve. Now with that bell-shaped curve, what we find right in the middle of it, we know will be our mean, median, and mode. And if we can, with quantitative data that is symmetrical, we would like to use the mean to reflect our measure of central tendency. Now the empirical rule tells us that within a spread of one standard deviation from that mean will occur approximately 68% of our observations. If I go out as far as 2 standard deviations, then we're talking about encompassing 95% of our observations. And by the time we get out to 3 standard deviations from our mean, we're looking at 99.7% of our observations. Now those numbers are extremely important. They're going to be something that we have to remember. We'll see that committing those to memory will be crucial when trying to answer certain examples. So what we have here is a question where we're going to apply that empirical rule to the dataset 1.4 that we just calculated our measures of variability on. So in that dataset, we should find that almost all of those Coke bottles should be filled to within what range? Now, it is very important to point out here that anytime we see that term almost all in this course, it will always refer to 3 standard deviations. So what we want to know here, talking about almost all, is within 3 standard deviations, what should we see as a low value, 3 standard deviations below the mean, and what should we see for a high value, 3 standard deviations above the mean? So if we could somehow know what the mean and our standard deviations were, we could answer this question. Well, we did make those calculations in our dataset 1.4. We found that the mean was approximately 591.06 milliliters, and the standard deviation was approximately 0.43 milliliters. Well, on the low end of that spectrum, we should have our mean of 591.06 minus 3 standard deviations. On the high end of the spectrum, our mean of 591.06 plus 3 standard deviations. Or we should have that 99.7%, or almost all, of our Coke bottles should be filled to within the range of 589.77 milliliters up to 592.35 milliliters. If, according to the same data set, we're asked approximately what percentage of bottles will have more than 591.92 milliliters, well, the first thing we're going to want to do is to figure out how many standard deviations away from the mean are we talking here. So what is the significance? Why did they specifically ask us about 591.92 milliliters? Well, what we know is we have a mean of 591.06. They're asking us about the value 591.92. If we check what our deviation from the mean is there, we find that we have a value of 0.86. And what we should note is that 0.86 is exactly 2 standard deviations above the mean. Well, what do we know about two standard deviations? We know within that interval of two standard deviations from the mean, we should see 95% of all of our data. What's this question asking us here? What percentage of bottles will have more than 591.92? Well, if we know that 95% of the data is contained within two standard deviations of our mean, that leaves 5% of the data lies outside of that, and not all of that 5% is on the high side. Half of that is on the high side and half of that is on the low side, which means that we should see approximately 2.5% of the bottles being filled to more than 591.92 milliliters.